Here's a look at the 2+ hour 18650 endurance plane. So once again, it's just a simple rudder elevator throttle, obviously polyhedral, really basic sheet balsa glider. Alright, so a little bit of design philosophy here. Obviously this is not the most optimized airframe for the task. The nose could be pointier, it could have a little more wing area, the wing could be built up as opposed to solid sheet. It could be a more optimized airfoil. There are all sorts of small ways this thing could be done better, at least from an aerodynamic standpoint. But the reason that I keep building them out of sheet balsa and sort of doing them the way that I've been doing them is because this has been an excellent trade-off of durability and flyability. Flyability is the ability to get out and fly even when it's windy, even when it's rough conditions that you wouldn't necessarily be able to handle a lighter, floatier airplane, or at least the lighter, floatier airplane will have a hard time flying efficiently. This thing can still maintain pretty good performance even when it's like really windy. And so that's a big point, is stick time, is being able to get it out and fly it and practice and just become very familiar with the model. That is a big help. So power system-wise, it's running a completely stock speed controller. This one is not modified for the low voltage modification. The reason for that is because the cell is going to go down so low just in the course of a normal endurance flight that we don't want to have anything artificially boosting it. We just want the voltage to drop naturally, and when the thing starts to shut down, it's time to land because it is tanked, it's over. It's 2 servos buried down in the nose, it's a receiver, it's a voltage booster. It's full cell voltage coming from the speed controller here through the throttle cable to the radio unit here. 2 push rods out the tail. The wing on this one is, again, the same design. Carved sheet balsa, 3-inch cord, 33-inch span, about 1/4 of an inch thick. It's got the same steel joiners. These I wrapped in fiberglass thread instead of the Kapton tape that I used on later models. I switched to the tape because the fiberglass sucks, but that's how it's done, same deal. Butt joint, CA, steel joiner in the slot. 2mm carbon fiber spar. This is actually a couple of laminated sheets from the 6x5.5 prop package that I originally ran on the model. Once again, very basic, simple way to make a wing. The nose on this model is flat because if I want to mate a spinner up to it, I can, and it matches pretty well with the profile. Alright, here are all the components that I used in the original 2-hour build, or 2+ hour build. This is an M35A cell. It's kind of an antique by now. There are much higher capacity 18650s on the market, so future endurance attempts will not use this, but this is the actual cell that I used for that flight. It's a completely stock. There's nothing modified. There are no board modifications. I do obviously replace the leads. I usually remove the outside heat shrink and wrap it in something a little lighter or more heat permissive. But for the most part, it's a completely stock board. There's nothing modified. There's nothing changed. It's right out of the package. It just works all the way down to sub 3 volts. Interjection. I want to point out that the 20 amp version of the speed controller does not work on one cell. Repeat. The 20 amp version does not work on one cell. It will not power up below about 5 volts. Here's the motor. It's a completely stock, Emax Eco 1407, 4100 kV. This is like 14 grams. Here's the prop. Again, it's a completely stock APC 6x6E. It's black plastic. It's not carbon fiber. There are carbon blend props available that look just like this. I like them better because they are lighter and they're much stiffer. but this I think is the only option for the 6x6E specifically. Servos, there are two of them. They are DHV56MG. I get the DHV, the high voltage, because the idea is that if I run it on 5 volts, which is at the bottom of its voltage range, it will generally produce a little less power and speed, but it will also consume a little less power, on the input side. And that just helps with the absolute minimizing of, the amount of energy used overall during the flight. So that's a little bit of the logic there. Here's the voltage booster that I use. This is an Adafruit mini boost. This reliably takes in the single cell voltage and boosts it to 5 volts and keeps it there no matter what realistic load I put on it. Works good. This is the alternative voltage booster. It has a little bit bigger of a footprint than the mini boost. You can see there it's a slightly bigger board, and it has a slightly higher dropout voltage, around 2.5 volts, but it works fine. It does have these selectable resistors, or these select resistors here, that make the output voltage selectable. So you can choose 5 volts, 8 volts, 9 volts, 12 volts. And so it's a neat little project board all by itself. And it's really cheap if you buy them in bulk. You get an envelope full of these. It's a serial receiver. It gets flashed with PWM firmware. So it converts 2 or 3 of the pads to single PWM channels. The remaining 2 pads are still power. It's got this tiny flat chip antenna. Saves a lot of space, saves a lot of weight. Looks easy to doubt, but it works just fine as far as I can tell. Overall, this setup, obviously, it's a little bit of assembly work. You have to really put stuff together and wire things up, but the basic components are unmodified. You can literally just buy all this stuff off the shelf. There's nothing like custom modified or custom made. Not even like the motor is not even rewound. All the drive system components are relatively oversized compared to the amount of continuous power that they have to run. That's really just a move to improve the efficiency, because things generally tend to work less hard when they're working less hard, if that makes sense. They waste less power. So despite running on only a single cell, it does have plenty of performance. The top speed in level flight is surprising. It doesn't quite have unlimited vertical, but it does climb aggressively at full throttle. So the basic controls obviously are rudder, elevator, and throttle. There is also, in addition, this slider on the back that adds a little bit of elevator trim up and down, and that's just sort of a speed control to sort of trim the airframe in for a specific speed, independent of this stick and the trim. So a key component of the efficiency flying is the throttle curve. There are 2 of them. You'll notice one goes from 50 down to 0, which is weird, but it's like that because the ESC is set to bidirectional mode. and that's position 0, so that's a full throttle range. That's from 0, full stop, to maximum forward. The second throttle curve, position 1, is designed to maximize the stick resolution over the useful RPM range of the motor. And so what I mean by that is I get the motor kicked off right off, like on the first click of the ratchet here, the motor is already running. And it runs only to a maximum of about half power, or half throttle. And so it's a much narrower band of power overall. And the idea there is that the model really only needs a little bit to fly, and I want to be able to maximize my control of the range that I'm actually using versus having to sort of live down in this small range here to control the full power. I can now use the whole stick travel. So the reason I have all these electronic components staged and ready to go is because I'm building another model. I will be assembling all this stuff into a working model at some point here. I'll try and get some of that on video, but what I'm noticing is that it's really, really difficult to get video of actually soldering and doing the assembly work. So we'll see.